I'm Brenden Lake from NYU, and my talk is called Concepts and Questions as Programs. So as Andy mentioned, I'm a cognitive scientist, and I study computational problems that are easier for people than they are for machines. So there's been a lot of exciting recent progress in AI and machine learning, yet for most types of everyday cognitive abilities, people are still better learners and thinkers than machines are. And by everyday cognitive ability, I mean things like concept learning, asking a question, understanding a scene, or tasks that involve creativity, general purpose problem solving, reasoning, language understanding, speech recognition, and so on. And my research has two main goals: to better understand people and also to try to build a more human-like learning capacity in machines. And today I'm going to focus on two of the abilities on this slide. I'm going to focus on concept learning and asking questions. For concept learning, for me, the motivating question is, how do people learn such rich concepts from very little data? Imagine this is your first time seeing a Segway. You just see that image of a Segway at the top of the screen. That single image might be enough information for you to basically get what the concept of a Segway is. And you can recognize it again, even if its features or its appearance have changed, and be able to rule out other distractors that share some properties in common with the original image. So this ability is often called one-shot learning, and it's been of interest to cognitive scientists and AI researchers for a long time. In addition to learning very quickly, people also seem to learn very rich representation. So by the time that you can recognize a Segway, you can do many other things with that concept, with that mental representation. You can use it to parse an object into its most important parts and relations. You could use it to generate new examples. You could sketch your own version of a Segway. Or you could even generate a new concept. So if you take a Segway and a motorcycle and a unicycle and combine them together, you could think up or imagine new types of vehicles like the one on this slide. So how do people do this? How do they learn rich concepts from small amounts of experience? And it's interesting to contrast this with some of the biggest breakthroughs in machine learning and AI, particularly in the space of object recognition, where we have these deep neural networks that are trained on very large amounts of data. So this is the famous AlexNet deep convolutional neural network. And it's trained on the ImageNet task, which has 1.2 million images and about 1,000 images per class. And the model is very large. It has 60 million free parameters. And below, I'm listing some of the more recent versions that won the ImageNet challenge in the years after AlexNet. And these models are trained on very large data sets rather than on small data sets. And also, their primary focus is on classification as opposed to some of the other abilities I just had on the slide. Yeah?
So a common thing with deep learning is most people with deep learning give very nice, cute test cases. You can show pathological cases as well too. I mean,
yeah. In one of the case studies I'll go through, I'll show some stimuli that they don't seem to match people's judgments. And the second part, which is going to be shorter, is going to be about asking questions. And I'll give you a little teaser about what I mean by this. So when people are asking questions while learning, this is a form of active learning. And if you imagine you're a child and you're learning about different types of instruments, and you have these objects in front of you, you might ask questions like, and you don't fully understand how instruments work yet. You might ask, how does a saxophone make a sound? Or what's the difference between the second object and the third object? What's the difference between a trumpet and a horn? Or what features are especially important about a French horn? And in contrast, there are active learning systems in machine learning. So are you ready for what the standard robot questions look like?
What's it made of?
Nope. So most of the time in active learning, the question has this form: what is the category label of this object? And what is the category label of this object? And what is the category label of this object? And I'm being a bit unfair. There has been interesting work in active learning and robotics about asking richer types of questions, but I think it's fair to say that we have no algorithm that matches the sophistication and the richness of the human ability to ask questions when learning new things. So here's the outline of what I'm going to talk about today. In concept learning, I'm going to go through two different case studies, one on handwritten characters and the other on recursive visual concepts. And then I'm going to talk about a third domain, which is active learning with richer types of questions. The title of the talk is Concepts and Questions as Programs. And by programs, I mean expressions in some structured description language that's a lot like a programming language. And we're going to think about what the structure, can you represent each of these domains with a form of program? And what is the structure of those programs? What are their semantics? And that's going to be one of the unifying themes across these different domains. But I want to add a disclaimer that by the end of the talk, there isn't going to be a single piece of software that you can run out of the box on many different types of data sets. So the main goal is to try to study the principles and the representations that people might use to solve some of these problems and use that to inspire more human-like learning algorithms. But it's still going to take work to try to use these ideas and these algorithms in different types of domains. So it's not an out-of-the-box approach yet. And there's an alternative title for this talk. Instead of about concepts and questions as programs, I could have called it or named it after these three key principles that are going to thread through the different case studies that I talk about. And these principles are compositionality, causality, and learning to learn. And I'm going to tell you a bit more about what I mean by these different things. And I think learning programs is a very natural way to implement these different principles together in a single type of computational approach. But the principles are more general than this particular approach, and you can imagine integrating them into other types of machine learning and AI paradigms. So this is the other way you can think about some of the ideas here. OK, so let's get into the first case study, which is about handwritten characters. So this work is joint with Josh Tenenbaum and Russ Solokhudinov. Josh is at MIT and Russ is at Carnegie Mellon, and it recently appeared in the journal Science. So reminding you about this question, how is it that people learn rich concepts from very little data? We wanted to study this ability, and we wanted a testbed domain that had certain characteristics, where we wanted the concepts to be natural and high-dimensional and have enough structure of real-world objects, but we also wanted them to be simple enough that we had a reasonable chance of building a computational model that could see most of the structure in the stimuli that people can, and we could compare people and machines on a roughly even footing. And we also wanted a domain that could help us generate insights that were more general than that particular domain. So the domain we picked is handwritten characters. And if you're a machine learning person, you almost certainly know about the MNIST data set, which is a standard benchmark. And in terms of concept learning, there's 10 concepts, which are the 10 different digits, 0 through 9. And there's 6,000 training examples of each of the digits in this data set. And we have a new data set, which we call the Omniglot data set, which you can download on GitHub if you want to try it out. And we think of this as the transpose of MNIST, or the more human-like version of MNIST. Because rather than just have a few concepts and a lot of data points for each one, we have many different concepts, 1,600 different concepts, and 20 examples of each of them. And the concepts are picked from 50 different alphabets, some of them real, some of them synthetic. And there's just a small number of data points for each one. So I showed you these interesting things you can do with a concept like a segue. And it turns out you can do a lot of these interesting rich abilities with simpler concepts like a handwritten character. So first of all, let's see if you can learn a new character from a single data point. So everyone take a look at the image at the top of the screen there. And in the grid below is another example of that character written by somebody else. So I'm going to move my laser pointer across the screen, and I'm going to ask if you could clap your hands if I touch another example of that character. Is everyone ready? All right. So that was some excellent one-shot learning. You clearly didn't need thousands of images. Just a single one is enough. And in addition to doing classification from a small amount of data, You could also parse it. You know about efficient ways you could produce it. You could generate your own examples of that letter. You can even generate new letters in the style of other letters. So your concept of a letter is a lot richer than just the ability to do recognition. And we want to study that representation and try to figure out what it could be. So an interesting part of the Omniglot dataset, in addition to having the images, we have a little movie showing how it was produced. So it was drawn on Mechanical Turk by a bunch of different volunteers. And the different colors here are different pen strokes that they use, but they were using their computer mice. And you can see there's a lot of consistency in how people draw this novel character in terms of where they start, their movements, how many parts, what are the parts. And so here's 20 people drawing this letter for the first time, and they draw it like this. I'll show you another example. For me, this letter clearly has 4 parts, and almost everybody agreed. And there's also a lot of consistency in the way that people decided to draw it in terms of where they started, the movements, and what direction they moved, and so on.
Question. For this particular one, does it matter whether you had Western European or Middle Eastern people doing it? Left, right versus right to left?
Yeah. We have a bunch of data for that where we know the country for each person. We didn't do very much with it, and I think we should. But at least the starting at the top of the character and moving left to right seems to be a very universal thing, even if the language is actually written right to left, unless you're left-handed, and then you do it the other way. But that at least seems to be pretty strong across other languages. I'll show you one more movie of 20 people drawing this letter. So when we saw this data, it seemed like people weren't just doing something arbitrary. They somehow inferred a structured representation where they were able to efficiently produce it. And it was something like a motor program, perhaps. So we took this idea quite literally and developed a model that we called Bayesian program learning. And the main idea here is concept learning is a type of program induction. And there's some key ingredients for learning good programs. And I'll tell you a little bit about what these ingredients are. I mentioned them earlier: compositionality, causality, and learning to learn. So the first ingredient is compositionality, and this is this old idea that representations can be constructed from a combination of parts and primitives. So if you know about vehicles and you know about wheels and handlebars and posts and seats and motors and how these different parts relate to one another, when you see a Segway for the first time, if you parse it into these parts and relations, it gives you a rich representation that can help you pick out new examples of the same concept. So that's the compositionality idea. The second ingredient is about causality. And it's this idea that generative models at an abstract level can capture real causal structure where the data comes from in the world. And this is an observation about digits from Hinton and Nair, where they pointed out that these twos, they differ a lot in pixel space. They may not share many pixels in common, but they're very similar in motor space. Basically, the same movement produces all those different twos on the screen. And that could be a better representation for generalization. You can also think about a concept like a tree, where you could find features to help you recognize it and identify trees, but there's also some deeper causal structure there about how trees grow in terms of branches growing and then the branches themselves branching. And we have a lot of additional knowledge beyond just features that we use to recognize it. And the third ingredient is what we call learning to learn, which is this idea that you become better at learning concepts as you learn more of them. So in terms of handwritten characters, the model learns a lot about the structure of letters in general. So it's trained on about half of Omniglot, where it gets a lot of experience with letters and knows about how many strokes tend to be in letters and where the strokes tend to start. Like the first stroke tends to start in the top left, and the second stroke tends to be a little bit more diffuse and so on. It learns about motor primitives in terms of some basic movements that people tend to use when they're producing letters. It learns about how much sort of affine transformation there is from one person writing it to the next. It learns about different relations and when strokes tend to attach to one another and what the different sort of types of relations are. So those are what we mean by learning to learn. With this type of knowledge, it can help you become a better learner. So the model is pre-trained on letters from other alphabets and then tested on new ones. So the idea of this Bayesian programming learning model, or the BPL model, and also the code's on GitHub if you want to try it, is that we have a generative model or a program for generating new letters. And you can run it and sample new types of letters, where the first step is to sample how many parts you want, which are the strokes. Then for each stroke, you sample how many subparts you want, which are the primitive motor actions that make up a stroke. You then sample relations, how the different parts attach to one another. And then you return an object, which itself is a piece of code, another program. So that's a program that generates types of letters. And it returns a subprogram that generates different instances of that letter. So now every time you run this program, it adds some motor noise, some differences in terms of exactly how the strokes are laid out. It adds transformations, and then it renders it down into a binary image, the motor trajectory. And you can produce different variations of the same letter. So that's the structure of the model. It's a full probabilistic generative model that samples types, and then the types can sample tokens. And we can use Bayes' rule to reason about what's the probability of the program's theta given an image I. So all the model sees is a new letter, just the binary image, and it has to reason about what's an efficient motor program to have generated this image that I saw. How is it likely to be generated? And we can treat this as a problem of Bayesian inference. So I'm going to show you a few of the things that the model can do. And in the paper, we go through all of the tasks on the screen. But I'm just going to show you a little bit from a few of the tasks. The first task is the generate a new example task. So here, people were shown a new character, like the image at the very top left of the screen. And we asked 9 different people on Mechanical Turk to produce a new example of that letter. And then we asked the model to do the same task. We showed it exactly the same binary image. And then we asked it to produce 9 new examples of that letter. So you can treat this as a visual Turing test. Can you guess which of these grids is the model and which of these grids is the people? So I'm going to poll the audience. I'm going to ask you, which is the machine, A or B? So we're going to look at the top left one over there. So one of those grids of 9 is people, and one of them is the machine. So which one do you think is the machine?
A.
B. OK, well, just for show of hands. Any votes for A? OK, a few for A. B? All right, very good. Let's try the one in the bottom right. All right. Everyone make their prediction. Votes for A? Votes for B? OK, this one's pretty evenly split. So I'll show you the example. So the right answer, so it was A and then B. It can be tough to tell. We actually ran a visual Turing test like this, where we gave people 50 trials where they made a prediction and they got blocked feedback. So every 10, we told them how well they were doing. And on the y-axis here is the identification level, basically the accuracy of the judges in a visual Turing test, meaning that if they were 50%, they didn't have an ability to discriminate. So the red is the BPL model, and it's very close to chance performance. But then if we lesion some of the key ingredients that I was telling you about, where we lesion aspects of the learning to learn, or we lesion aspects of the compositionality, it becomes easier to tell that it's not a human drawing the letters. So I'll show you what those look like. So here, the full model is the left column. The middle column is a lesioned a model that doesn't have compositionality. So it tries to do everything with one giant stroke. And some of them look OK, but other examples look kind of funny. And the last is if you lesion some of the learned parameters from the data set. And in this case, the model is way too stochastic. And again, people can realize this is not how a person would draw these things. So showing the importance of the principles. Another task we looked at was one-shot classification from a set of good examples. And this is the same demo that we did earlier. So we ran people in the same task. We show them one image of a new character, and we have them try to pick out another image of the same character. And so y-axis here is error rate in the classification task. And pink are people. They're around 5% error. The red is the Bayesian program learning model, and it was similar error to the people. If you lesion the learning to learn and the compositionality, the model gets worse. And we also tried various types of deep learning models, including a deep convolutional neural net that was trained on 30 other alphabets and then tested on these, or a deep Siamese convolutional net, which is a little fancier version, and a hierarchical deep generative neural network. And in each case, it was, the error rate was significantly higher than our model and also worse than people. So it's, even though these are very good models for recognition with a lot of data, it's a lot more difficult to perform well when you just get a single data point, even if they're heavily pre-trained. So this was with a set of held out alphabets. So it was trained on 30 and evaluated on somewhere between 10 and 20 additional alphabets.
So how could we get your error rates then? Like if you just missed 1 out of 30, that would be like 3% error rate. So you can't get very low in this, right?
Yeah, so that's averaged across a bunch of different trials like that. And I think what's interesting about this is people have been talking about the importance of generative models and how good generative models would be for if you could produce the data, you could classify the data well. But by and large, discriminative models have mostly won the classification game and have beaten generative models in most types of classification tasks. And I think a contribution of this work is to finally show that the power of generative models for classification, especially in this small data setting and if you get the representation of the data right. OK, one more task, and I'm just going to briefly flash up a couple movies. So here's people drawing these 20 different letters. I showed you 20 different examples of this letter, and also the model drawing the same letters, trying to predict how people draw them. So there's some similarities in terms of how the model decides to draw letters and the way people decide to draw letters. And we did an analysis of this, but I'm not going to go through the details of that. OK, so that's the first case study. So let's move on to recursive visual concepts. And this is joint work with Steve Piantadosi at the University of Rochester. So the main idea there was concept learning as a type of program induction. But if you think about the space of possible programs, the different types of programs that one could write, a motor program is a relatively special case. It has unusually concrete and embodied semantics. So the actual parts of the program can be grounded out in terms of motor actions. And not all programs are like that. Certainly, only a small set are. So if the mind can genuinely write a program to represent a new concept, we wanted to know what are the limits of this ability? How general is this ability to write a program to represent data? And in particular, can it learn more abstract types of programs? Could it learn classic programming techniques like recursion? Could it learn recursive programs? And I think recursion is interesting because it's not just an abstract concept. It's, of course, an important part of language and thought, but also certain types of natural concepts that we reason about and learn about in the day-to-day environment. So here's a type of broccoli or the feathers of a peacock or an ice cave or a tree are all recursive concepts that have this underlying fractal structure to them. And we were curious to see whether we can teach people very abstract versions of things like this. And again, going back to this idea of causality as an ingredient and whether it influences your perception, if you take the image at the top of the screen and think about what is it more similar to, A or B?
B.
Well,
it's a plastic tree.
That's absolutely. But you knew it was a plastic tree, which is interesting. Yeah, so I think, we got one answer for B. I bet there was also people that wanted to pick A. And the reason why is because you have causal knowledge here. You know A might grow into the thing at the top of the screen. Whereas B is a similar color, a similar shape, a similar size. It's a type of mistake that the deep convolutional neural network might make. But It shows the importance of causality in terms of your intuitive similarity metric in terms of the basis of your concepts.
You don't hang with botanists very much, do you?
No, I don't. Why?
Well, just to let you know, in the 1980s, Richard Voss at IBM, when he was doing some of the first fractal imagery, put up what in the computer community felt was great-looking fractal mountains. And the first thing Voss said is, do not show these things to geologists, because geologists look at geomorphology vastly different than the naive public do. And similarly, you know, you and I might think of that as a Christmas tree, quote, a Christmas tree, but the reality is a botanist will say that's a particular type of spruce or some other species or something like that, even if it is.
I certainly believe that. Are you a botanist? Are there any botanists?
No, but actually,
we have
a friend of mine over here. We have serious botanists.
Okay, that's good to know. Well, I apologize for getting
you should be warned about Voss's. He wrote about this in the 80s about showing images like that to professional audiences. It makes a difference.
All right, thanks. Okay, so we wanted to explore the limits of this ability to induce a program from data. And we wanted to push the boundaries of the human capacity in a few ways, where we looked at these abstract, recursive visual concepts. We varied the number of examples, where we showed people just one or a few examples from the concept. And we also tested a range of different ways that people could generalize in terms of classification, and also generating new examples of the underlying program. So here's the setup. We told people that there's a surface that was infected with a new type of alien crystal. And it was growing for some time. So the before image shows the surface, and the after image shows the crystal growing on the surface. So that's what this crystal looks like. And we asked them to try to predict what the crystal will look like if you let it grow for some additional period of time. So take a look here. Again, I'll ask for your opinion. Do you think this crystal is going to grow into A, it's going to grow into B, or going to grow into C? So votes for A, votes for B. Very good. Yeah, it's a bunch of computer scientists, so it works very well. And let's try another one. So same setup. Crystal's been growing for a while. You have the before and the after. What is it going to look like as it continues to grow? Votes for A? Right. Also very good.
Could you back up the slide?
Mm-hmm.
I'm not sure, but it wouldn't surprise me if a good argument couldn't be made for C in the sense that your example only shows one generation of triangles springing up from the only line segment they can spring up from. But the next generation, triangles might be springing up from duplicate line segments into the same space and interacting in some way that would not produce B. Yeah. The lowest generation of triangles in B very cleverly grew, cooperatively from both of the adjacent segments, whereas something like C might be an example of something where they compete with each other.
Or another argument is that C is 15 steps down, and between the first two, it's 6 steps, and we didn't see the erasure.
Okay, whatever.
Yeah, so I'll explain how they were generated in a second. And so there's a sort of coherent program for B, and C maybe there is, but B definitely has sort of a nice compression to it. Yeah.
While it might erase lines higher up, I don't think it could erase lines on the bottom. If you have triangles growing.
Okay, good point.
Yeah. So it doesn't actually. I'll explain exactly how to grow these things. So we wanted a language to represent these different types of simple recursive visual concepts. And the language we chose are L systems and turtle graphics. So you might know L systems, Lindemeyer systems from a while back, and they're related to context-free grammars. And turtle graphics are from the Logo programming language and still used, I think, to teach intro programming. And the idea behind turtle graphics is turtle is a little dot on the screen, and it has an orientation, and you can give turtle commands, and you can have turtle trace out an interesting contour like any of the ones on the screen. And I'll explain how our version of Turtle works. So Turtle has 4 different commands that you can provide. The legend is on the top right of this slide. You can tell Turtle to make a right turn, which is a plus sign in the symbolic language. A left turn is a minus sign. F is the command to go straight, and G is another command that means go straight, but they're going to have different rules of evolution. And so that's the legend for this simple Turtle language. And the L system specifies the angle in which Turtle turns, so it has a consistent angle, a start symbol, which is always F, and then rewrite rules for the strings, so F becomes this more complicated string, and G doubles, essentially. And the difference between an L system and a context-free grammar is that at every step of at every iteration, you apply the rule in every possible place, rather than just applying it once. So in the first iteration, F becomes rewritten as that string on the right-hand side, F minus G plus F plus G minus F. And if you trace that out, starting at the left-hand side of that canvas, you draw an upside-down triangle. And then if you apply the rewrite rules again, you end up with this longer string, which looks like the image at the bottom. So that's the language we're going to use to represent these different concepts. And we did a classification experiment, which was a lot like the demo we just tried. We used participants on Mechanical Turk. They saw 24 different fractal concepts. They didn't get any feedback. They had 6 choices where the distractors were made by taking the last step of the examples and then using a different rewrite rule rather than the correct one. And there was 2 conditions. There was a latent condition where they just saw the before and the after step of the growth. And there was a stepwise condition where they saw every step of the growth. So there's more information there. And that's similar to a visual recursion task that's been studied by Martin and colleagues. So there's a psychological literature about this task and whether people can do this type of visual recursive inference.
I
Yeah.
have a question about why do the segments get shorter, since you're already saying for...
Oh, yes. So all the images are normalized so they fit nicely into the little window. So when you go to additional level of recursion, all the steps, like essentially the figure gets a lot bigger, but then you normalize it to fit in the window. That's a good question. So I'm just going to flash up the 24 different stimuli, and they didn't get feedback after every judgment. And yeah.
Backing up to the last person's question. There's a scaling issue that I didn't see in your rule definition, where other generation, a line is a certain length, but the next generation down, a line is only half that length.
Yes.
How was that conveyed in the?
Yeah. So they're renormalized to have a common width, so they all fit nicely centered to span the bottom of the canvas.
But as it's being drawn, somehow the second generation, it knows not to draw a line the same length as it did before.
Yeah, so it draws in some abstract space that grows a lot bigger in each iteration, and then they're all projected down into a normalized space.
Because you're doubling the F, right? You're replacing F with FF, so it goes twice as far.
Yes.
And then FF becomes FF.
Yeah, so then you divide by 2 if you wanted to get it back.
Okay.
Yeah, so chance in this task would be around 16% correct, because it's 1 out of 6. People were much better than that. They were about 65% correct, so they seemed to make judgments, classification judgments, consistent with the underlying program. And interestingly, there was no difference between the stepwise condition and the latent condition, where they just saw the before and after. We can make a Bayesian program learning model of this, where we have a metagrammar M, which is a context-free grammar that generates L systems. So there's 2 layers of grammars here. We have a grammar, which is a little complicated, and I won't go into the details of how that works, but it generates the rewrite rules of the L system. And so it forms a prior, in a Bayesian sense, over the space of L systems. The L system can then, you sample how many iterations you want, which is the D variable over there. And that determines what the image looks like. And we render that down into a binary image. And that's the generative process for images from this model. And then we can invert the model and talk about, if you just give the model the image, reason about what are the possible concepts, these L system concepts, and iterations given the image that you saw. So reason about the posterior distribution on L and D given I. And we use an MCMC algorithm to search the space. So there's an important note here where the model has some clear advantages over people in that it has exactly the right programming language, right? And it knows about this special class of growth-like L systems, but it doesn't know about anything else. And so people can infer programs like these, it's because their programming language or their language of thought is sufficiently rich that it includes things like this and many other things. So I think it's very interesting if people are able to behave in a way that's even partially as good as this model is, which has a lot of advantages. We also looked at other measures of perceptual similarity. You can think of these as alternative models. We looked at modified Hausdorff distance, which is a classic distance measure over binary images. It basically looks at the pairwise distance between pixels in two images and averages over all the different pairwise distances. And what's interesting is if you try to make the generalization to the next step, it always picks the image that has the smallest perturbations to the original. So the one the top and middle is the closest match to the one on the left, and it's quite far from the right answer, which is the middle at the bottom. We also looked at a pre-trained deep convolutional net. So this used to be a state-of-the-art object recognition system, or it was a few years ago. And it behaves quite similarly, where it likes small perturbations, and it's quite far in terms of the feature space from the underlying the real next iteration of the program, which is again is shown at the bottom middle here. So if we plot the models on this slide, we see that chance performance, again, around 16% correct. The ComNet and the Hausdorff distance are around chance, definitely not better than chance. The Bayesian program induction model is at 100% because it has exactly the right language. If you do inference for a sufficiently long time, it will find the right answer and be able to do the classification task successfully. So why aren't people were at least generally consistent, although variable, with this model, but why weren't they perfect like the model? Well, my hypothesis is that there's a failure of search here. And what you can do with the model is it's a sampling-based inference procedure where you keep drawing samples until it finds a region of the posterior which fits the data well. But sometimes it never gets there. And you can actually fit the number of samples that the model takes so that it matches the human level of accuracy. And at least intuitively, that's how I feel when I look at these stimuli. Sometimes I can get the recursion, I get sort of a simple story, but other times you just feel like you don't find it. And you can model that potentially by having limited amounts of sampling, and which will sometimes find the right hypothesis and other times not. And if you do this, the model can do a decent job at predicting what fractals people found easier or harder to learn. It gets around the 0.57 correlation with the aggregate accuracy for the 24 different concepts. If you fit it to the overall accuracy level and then try to predict which concepts are easier or harder to learn. So there is a heuristic that is closely related to the idea of being a recursive visual concept or an L system, but isn't quite the same thing, which I call the look for a smaller copy heuristic, where if you take iteration 2 and look for a smaller copy of it in iteration 3, that will actually do very well on our task. So it's closely related to getting it certainly means you got some recursive structure, but it doesn't mean you got the L system in the full extent. So we did another experiment which was more unconstrained. It was a generation experiment. And again, there was a stepwise and a latent condition. We showed people, in this case, 3 different steps of this concept. And then we asked them to try to generate the next step, or to generate how it's going to continue to grow. And they were given an interface that looks like this, as a blown up version of step 3. And this is how the interface worked. It was, again, on Mechanical Turk. If you hover over a segment, you highlight it as green. And if you click on a green segment, it grows a little growth, which is the right kind of growth. So we limit them to looking at growths that look like the actual underlying program. And then if you highlight it again, it shows up at red. If you click it again, it goes away. So you can sort of pick where you want to try to grow the program from the previous step. We also gave people an all button, so if they clicked that, all the growths popped up. And we gave people a none button, and if you click that, they all went away. So you have this flexible, interactive display to try to grow what you thought this program would evolve into. Again, we did a similar experiment. There was a latent condition and a stepwise condition. They didn't get any feedback. There were 13 different fractal concepts. Not the full set of 24, because some of them, the segments got very, very, very small, and you can't really see them or click them. So we picked the 13 with the largest segments. And what we found was there's a few different ways you can measure accuracy. Each stimulus has a bunch of different choices. Each click is a choice in a sense. So you could look at, for each individual decision, was it right or was it wrong? Each click. And people were about 90% correct in the stepwise condition for each individual click. And they were about 70% correct in the latent condition for each individual click. We can look at a couple different baselines. If you're just a random flip a coin, a fair coin responder, that's the red line here, you get 50% correct. The deep convolutional net doesn't want to flip any of the parts, because the most similar image is the original one. If you just click none every time, you get around 57% accuracy. So those are the baselines. We also looked at whether people generated exactly the right example. And interestingly, in the stepwise condition, they did about 60% of the time. In the latent condition, they did around 23% of the time. And we have a bunch of different baselines here as well. So even the simplest stimulus had 22 different possible places to click. So if you're flipping a coin, you're never going to get the right answer just based on chance, because that's 1 over 2 to the 22 would be your chances of randomly stumbling upon the right answer for even the simplest stimulus. So the baseline's 0 in that sense, but if you click the all button every single time, which is the purple line, you do about as well as the latent group did, even though that's not exactly what they did. So the latent group's not better than that baseline necessarily, but the stepwise group does quite well at getting exactly the right example in that space. So I'll show you just 1 or 2 examples of what people's individual judgments look like. So this is the stepwise condition. They saw those steps. This is a particular easy example. And here, the ground truth is on the left. 14 people, everybody in this condition did exactly the right thing, which is good. In the latent condition, 6 people did exactly the right thing, and the other people did some interesting, not so correct things. But it's still, some of them were interesting and reasonable. Other ones, it looks like they just clicked the all button or something like that. Another example, so here's the stepwise condition for this fractal, where 11 people got it exactly right, and then 3 people did something different in the stepwise condition. But in the latent condition, only 1 person happened to get it right, and there was a whole variety of strategies. So to sort of summarize, I think there's a lot of variability in people's judgments, but I think by and large it was consistent with this Bayesian program learning model, and certainly better than these simple types of image distance metrics, also the deep convolutional network. And so I think it's interesting that people have an ability to learn these simple recursive visual concepts from a small number of examples. Okay, so now I'm going to get into the last case study. And this is about asking questions. And this is joint work with Anselm Roth and Todd Gurekis at NYU. And Anselm is a fantastic graduate student in the psych department, and he's been the lead on this work. And I should also say this is the least developed component, so I'll tell you about so the form of the model and where we're going with it. But we're still working on the final results and really sort of exploring the full potential of what we think this model can do. Okay, so I started with this slide earlier about human-level active learning, and the type of rich questions maybe a child will ask compared to the simple stereotyped questions that are common in active learning. And we want to think about what types of models would be capable of doing the same thing, asking rich types of questions. The main idea here is that we can model a question as a simple program where if you run the program on the world state, it will return an answer. And then thinking of a question is the process of synthesizing an informative program that will give you an answer if it was run on the world that helps you learn what you wanted to learn. And we wanted a test bed for studying this type of question asking. And so we wanted a task that allowed people to ask rich questions, any question they wanted. But we wanted it to be, again, simple enough that it was amenable to formal, in particular, ideal Bayesian modeling, so we could figure out exactly how good the questions are that they asked. So we picked the game of Battleship, which, as you can see on the box, is America's all-time favorite game. So if you want a refresher on Battleship, this is our variant of Battleship, where there are these 3 ships, the blue, the purple, and the red, and they have different sizes. They're somewhere between 2 and 4 tiles long. And they're hidden somewhere in this configuration. And there's 1.6 million possible configurations for where the ships could be. And as the learner, if you're playing the game of Battleship against someone else, you don't know where the ships are at all at the beginning. And you click on the grid squares, and then it colors in the tiles. And this starts to give you information about where the ships might be. So the dark gray tiles here are misses where you clicked somewhere and you didn't get any evidence. There was no ship there. You're just hitting water. So in regular Battleship, you sample all the way through, and then you make a guess about where the ships are. But in our version of Battleship, you had a special opportunity to ask any question you wanted about the game board part of the way through the game. So on Mechanical Turk, we gave people a text box that said, what do you want to ask about the board? You can ask anything. And they typed out a question in natural language. You might ask, is the red ship horizontal or not? And there were just a couple constraints. The questions had to be answerable in a single word. So you couldn't be like, tell me where all the ships are, because there's no one-word answer that will reveal that. And also, we asked them not to try to combine many questions together. Yeah, I'll get to that question later. Yeah. So here's the results for this particular game board. So this is what a bunch of different people in Mechanical Turk looked at. And here are the questions they came up with. And this was a lot of fun because we thought a lot about questions, and people surprised us and came up with better questions that any of us working on this project came up with ourselves. In particular, a few people like to ask, what is the location of the top left part of the purple ship? And that's a really good question for this board because it gives you a purple tile. And when you get that tile, it tells you something about the geometry of the whole ship. So it's a really good informative question. Other things people asked were, what is the location of one purple tile? Is the blue ship horizontal? Is the red ship 2 tiles long? We just had a very long list of a bunch of interesting things that people asked. And they saw 18 different configurations like this. And then we went through a sort of a painstaking process of coding the semantics of every question. So there's a whole bunch of different ways that you could ask the question, how big is the blue ship, right? You could ask, how many squares long is the blue ship? How long is the blue ship? How many tiles is the blue ship? There's a bunch of different ways to ask it in natural language that all boil down to just asking about the size of the blue ship. So all the questions, I think 700 something questions were coded into these functions that were encoded the semantics. And then we have the list of all the unique questions that people asked during Battleship. And I know you can't see that at all, so I'll show you a few examples. Some of the questions were like the location questions, very standard questions in Battleship. These are people that weren't creative at all. They just clicked, basically asked about particular grid squares, where the N is how many people asked the question. So they'd ask, like, what is the color at some particular tile? That's not a very creative question, but it was asked 24 different times. There was questions about different regions of the board, here are the questions about the size of ships. So a lot of people asked, how many tiles is the red ship, for instance? Or is the red ship 3 tiles long? Questions about size. There are also these demonstration queries, which are especially informative, asking about what is the location of one purple tile? What is the location of the top left part of the purple ship, and so on. So we did a second experiment where we showed different people, the same scenarios and gave them a list of 6 questions that were generated by other people. And we wanted to see if they had a sense of what's a good question or not in Battleship. So we asked them to sort them from their favorite question to their least favorite question. And they got the answer to their top ranked question, and then they had to try to guess where the ships were right after they got the answer. So, and their bonus was dependent on how well they guessed where the ships were. So they were motivated to do well. We also needed a measure of how do you know a question's good or not? So you can write down a Bayesian ideal observer model for Battleship, where H here is a hypothesis about the game board configuration, where the ships are. X is a candidate question that you might ask, and D represents a possible answer to that question. So you can use Bayes' rule to reason about the probability of a particular hypothesis given that you got an answer D to question X. And basically, it's just eliminating all of the configurations that are inconsistent with the answer to your question. So you can do this over all 1.6 million hypotheses if you're a Bayesian reasoner. And also compute an expected information gain of a question. So the expected information gain of a question X is your expected reduction in entropy from your prior to your posterior over the different possible answers to your question. So it's summing over all possible answers D to your question of the expected information gain of getting that particular answer to your question. And basically, it just boils down to good questions rule out a lot of hypotheses. And that's this normative metric of how good a question is. So if you look at people's rankings of the questions and look at the expected information gain measure from the ideal reasoner, on the x-axis is the preference of the ideal reasoner for the 6 different questions. Each scatter plot here is a different game board configuration. And the y-axis is the average rank score of people, where 5 meant everybody ranked it as the best question, and 1 means everyone ranked it as the worst question, and you can get an average in between that. And there's a nice relationship in most configurations between the ideal observer model's expected information gain and people's preferences. And the average correlation was about 0.82. So people seemed to know when there was a very good question and they picked it. And I think there's something right about this, where sometimes it can be hard to generate a really good question, but if you're in the audience of a talk and you hear a really good question, you often feel like, oh, that's a great question, even if you didn't necessarily think of it yourself. And what this is, if Battleship's anything like real life in that sense, people at least had a very keen understanding of when a good question was asked in Battleship. So what I think the most exciting part about this domain and what this project is trying to do is ask, can we build machines that ask richer, more human-like types of questions during learning? And there's a lot of benefits from this. If machines could ask better questions, they could learn from less data. And also, you could have a more natural type of interaction between humans and machines. So the main idea is that we can model questions as programs. Programs that when you run them on the world state, or the game board in this case, they return an answer. And there are some primitive programs that are essentially just handed to that come from the instructions of the game. They're very simple, like a program that asks for the size of the blue ship. So these are written in Lisp notation. So size is the function name, and blue is the argument. And so that's a program that asks for the size of the blue ship. We also have a primitive program that asks for the color at a particular tile or the orientation of the blue ship. And what's very nice is that these programs are compositional, and you can exploit compositionality to get richer types of programs that people actually asked as questions. So a lot of people asked, what is the total size of all the ships if you added them together? And you can get that, of course, by taking the basic programs that ask for the size of each ship and adding them all together. So you can use the addition operator as a means of compositionality to make that question, or to at least represent its semantics. You could also ask, are the blue ship and the red ship parallel? And this is just asking whether their orientation functions return the same answer. So again, compositionality, just like in some of the previous models, gives you this productive expressive power to synthesize richer questions from simpler ones, and helps to represent some of the things that people ask in the game. There's also, I think, learning to learn going on, where people didn't think of parallel for the first time when they were asking that question. They, of course, were transferring this existing concept from general world experience to this particular game. So there's definitely a component of previous learning influencing how you ask questions. Yeah?
Out of curiosity, was a Lisp used in the actual implementation?
And just to hammer home this point a little bit more, you can ask a lot of different variants of the same question, like how many ships are 3 tiles long? Are any ships 3 tiles long? Are all the ships 3 tiles long? And for this, you can take the same basic program, which maps a function that checks whether each ship is size 3, and by changing the outside operators, by either adding up all the results or checking if the sum is greater than 0, or checking if the sum is equal to 3, you can represent all these variants of the same question by just changing the outer operators of an inner function. So the compositionality buys you a lot. So we actually wrote a simple program for every question in the data set that people asked. And then we wrote a context-free grammar that generates every single question that people asked, and many other questions. So every question that people asked is grammatical, as well as many other possible types of questions. And of course, that's very hard to parse, but I can give you a little intuition about how it works. So there's non-terminal symbols, and the base symbol is an answer, right? So every program returns an answer, and this represents basically the return type of the program. An answer could be a Boolean, or a number, or a color, or an orientation, or a location. So you could transform the A symbol into any of those. And then let's say you pick a Boolean. Well, maybe it's the result of an equality operator between 2 colors. So you might pick equal CC. And then you might figure out functions that return a type of color. And then you can represent things like, is there a red tile at A1? And that's how you generate it, with sort of a context-free way from a set of rules. And this generates everything people asked and many other things. And you keep sampling until you ground out all the non-terminals with actual pieces of the program. So this is about where we are in terms of how this how we've implemented this algorithm. And we've already learned a lot of interesting things. So we first just tried to say, OK, what's the best question you could possibly ask? If you're going to optimize expected information gain, what's the best question possible? And ran genetic algorithms to search for the best question. And what came out to our surprise was interesting. So and you imagine someone might ask, what's the size of the red ship? Because they want to know the size of the red ship. But the model is greedy, and it wants to know the size of the red ship, but it also wants to know the size of the blue ship and the size of the purple ship, right? So it constructed basically these complicated polynomial expressions where it would say, give me 100 times the size of the purple ship plus 10 times the size of the blue ship plus the size of the red ship. And then it wouldn't stop there. It would ask about every other thing it could and string together this like totally uninterpretable polynomial thing, because it didn't actually use base 10. It would use some arbitrary coding scheme. Yeah.
If you generated every possible layout of votes as per the following algorithm, and then compared what you have against that list, what is the index of the solution? And you get the answer in one question.
Yes, that I guess would be a valid question. I'm very thankful nobody chose to ask that, because I'm not sure what we would have done. But yes. Fortunately, the text box is not that long. So that's what the model does. It's just looking for optimal questions. And so that's not what people did. for a lot of reasons. Maybe the length and the complexity of that question is too much. Maybe they're being nice to the answerer, and they say, I don't want to do that to anybody, and they try to answer this question. So we're trying to fit a model to sample questions, but human-like questions, and to actually put a probability distribution on this very complicated space of programs. And what we're using log linear models, basically, so the probability of sampling a question is proportional to this feature vector times whether or not each question has this feature. And the features are things like length and whether it uses various grammatical operators and so on. And there's a lot of really interesting questions in this space, like really truly novel things, like rather than just the top left of the purple ship, you can ask in the grammar, what's the top left tile of any ship? So if you take all the top left queries from all the different ship colors and then wrap that in a top left, then you can get an even better question that nobody asked. So we're really excited about seeing what the model comes up with in terms of its sort of best human-like questions, and try to use it to predict what people would ask on a new configuration, and eventually try to develop this technique so that you can apply it to different types of games beyond this setting. Okay. So the title of the talk was Concepts and Questions as Programs, and I talked about these 3 different domains and how we represented them in programs. And other domains that I think have a structure a lot like this are of course handwritten characters, but other causal, compositional, embodied concepts that are often symbolic, like learning a new gesture, or learning a new dance move, or learning a new spoken word, like an unfamiliar name. In all these cases, if you see a new gesture, like a high five or a secret handshake, and you've never seen it before, you could probably recognize it again, and you could even produce it yourself. And part of that, I think, is because you have this rich causal knowledge, this rich causal model of how that action could have been produced. You can produce it yourself. It's also compositional. There's some basic primitives behind it. I think all of these domains have some aspect of that in common. And so this approach might be especially fruitful for domains like that. There are also lots of domains where I think causality, which was the second principle, is very important for how we learn and use concepts. So what makes those 2 fractals in the same concept, what makes those 2 images of trees part of the same concept, or just the way you reason about objects in the real world, where you walk into a cave and you think about how it was formed, or whether it's dangerous to be in that cave, or if you think about a tree and you don't not just recognize that it's a tree or what species is it, but you think about what way is that tree going to grow? Is it too close to my house? If you think about all the different types of judgments that you can make, the different ways you use these concepts, I think you tap into the causal knowledge in addition to just a feature-based representation of them. And finally, for this sort of active learning as synthesizing programs idea, you can use programs to represent the compositional structure of the semantics of questions, and hopefully develop algorithms that can ask richer and more interesting types of questions for different types of learning scenarios and games. So to conclude, for the 2 parts on concepts, we asked this question: how do people learn rich concepts from very small amounts of data? And I think this Bayesian program learning approach helps to answer this question for a range of simple visual concepts. We talked about characters and also the recursive visual concepts. And the model embodies 3 different principles: compositionality, causality, and learning to learn, which were important for the model to be able to successfully learn programs from small amounts of data. And for the part about questions, how do people synthesize novel, interesting, rich questions when faced with uncertainty? I think this idea that you can represent a question as a program is a powerful one. And it again uses the principles of compositionality and learning to learn to get there. So that the last piece is a new project, but I think it's exciting, and I hope these ideas will be useful for developing more human-like learning algorithms. Thank you. Questions? Yes.
So at one one point earlier in the talk, you had a comparison between neural networks and your handwritten system for generating characters and doing recognition and so on. And I'm curious. So you showed that the Bayesian programming learning was better than convolutional neural networks, and you cited the benefit of being able to train on less data. But I'm curious because really there's two disadvantages the neural network is at. The first is that it has less data, and the second is that it's sort of like topology is set up such that it can only learn from this very general framework and it's not guaranteed necessarily to learn the concepts. So I'm curious if, like, given enough time, it would have eventually learned the concepts, or if it was actually set up such that it could never understand the concepts in the same way that you sort of hard-coded them in the system, that, like, you know, you attach characters in this way, or that, like, I guess, do you have any intuition behind that answer? Because I'm curious to what extent you can take these lessons and incorporate them into these deep learning domains.
Yeah, thanks. That's a great question. And I think it's still an open one to some extent, that we don't know if, given enough data, if it'll eventually learn the same representation that we have in our model, or whether it will take an infinite amount of data to get there. And certainly, if you train it on the 30 background alphabets in our data set, it doesn't get far enough to that type of to the accuracy that our model has. But you can make a very good classifier with a deep neural network from 10s, 20s, maybe 100 examples of each letter. So if your ultimate goal is classification, then you can do very well with that type of technique, but it doesn't necessarily learn the same type of representation. And particularly if it's a convolutional net, it doesn't generalize in any other of the other ways that we looked at here. So there's also a lot of other people working on building models of this data set and using sort of more generative type of neural networks, things like variational autoencoders, to try to build generative models of letters and that can not only do classification, but can produce new examples. And the samples look pretty good. They capture some aspects of what our model can do, but they also generalize in ways that our model does not, and people clearly do not. And sometimes it just produces totally the wrong character. So I think they're getting closer. They have a ways to go before we know if you can capture this type of generative process in a neural network. And part of the reason why it's so difficult, I think, is because everyone's training the model on just the images. And our model, of course, was trained on the images and also the motor representation. And it's hard to fit that type of representation, to train on that directly in a neural network, but I think it would have a huge payoff in terms of getting insight into the right sort of causal process, the right type of prior. And if you were able to encode that, you might be able to generalize in a way like our model does. So I think it's certainly possible, and I think if you train on the right type of data and incorporated the principles in the right way, you certainly might be able to do it, but we haven't quite gotten there yet with neural nets. Yeah.
Great talk, firstly. And so my question is kind of related to what he asked. So there's one common theme across all the different case studies that you show, that there's some kind of symbolic reasoning that you can use to get to the right answer. But think about scenarios where we ourselves as humans do not understand how the brain works. For instance, how do we generate natural images, not handwritten characters, but like natural images. So there's a lot of continuity around there. There's not enough discrete choices that you can make to get natural images. So in those settings, do you see any value of using Bayesian program learning, or should we leave the task of learning representations entirely to our algorithms?
Yeah, again, a very good question. And so certainly certain types of natural images, I think, have a causal structure that's a lot like what the Bayesian program learning approach can represent. And like those are things like the broccoli and the ice cave that have a sort of a clear causal story behind it. Of course, that's not every type of natural concept. There's a lot where you might look at an object and there isn't a clear causal story behind it. You may not know about what the right parts are in the same way. So for those cases, I think there could be value in both approaches, or sort of a synthesis of both approaches, where there's definitely discrete structure in lots of different types of objects that you may not have the same sort of domain-specific generative knowledge about, like chairs or animals or cars, where there's clear part structure that could easily be encoded in an explicit way in the model, but you may not know how to relate deeper part structure, the deeper causal structure to the actual image. So I think there might be a role to play for sort of feature-based deep learning style sort of representation learning to figure out how to connect up that latent structure that you know that is there for sure with the actual image. And you might be able to get both approaches to work together in a way that would highlight both of their strengths. So that's, we don't have systems that really work like that yet, but I think that would be a really exciting direction to go. I should also say something about scenes. Scenes in general are a case where I think having a richer causal model is especially important. And this is beyond just single objects, but you look at a scene like an audience at a presentation and you see many objects together interacting, right? There's a bunch of seats and people sitting in the seats, and you can tell why that scene is the way it is, or deep networks, or particularly the caption generating systems that try to understand the scene as a whole rather than particular objects, have special trouble putting the objects together in a coherent story. And if they see a scene that doesn't look like the type of training data that they have, they often generate captions that don't make a lot of sense if you run a deep caption generation system on like news images, so sort of obscure events, and the model was trained on vacation photos. It produces really terrible captions for these unusual scenarios for things that happen in the news. So there, I think there really is a need to have a rich causal structure to piece together the data that you see, and there's a special benefit for having representations that might look something like this. Yeah.
I was wondering, you expressed interest in the model in the third case, generating human-like questions. How do you define a human-like question?
That's a good question. The way we're evaluating it is to, it's a full probabilistic model, so we can actually evaluate it on a new battleship board that it was never trained on, and look at the set of questions that people ask and ask what's the likelihood of those questions under the model, and see if the model can predict people's questions with a high probability, as opposed to a simpler model or a model that takes a different type of approach. So we can actually we have some quantitative measure of what it means to be a human-like question. Can you actually predict people's questions in a novel scenario? So that's one of the metrics that we're going to use.
A follow-up to that, would there be a way to measure a human-like question that humans don't really ask? Like one that would be human-like, but most humans wouldn't think of?
Yeah, so that's the other exciting thing you can do with the model. You can then sample questions that nobody thought to ask. So what does it think the most probable things are that nobody asked? And we haven't quite gotten that far, but I'm very curious to see what it's going to do. Cool. Oh. Yes.
This might not be a fair question because it's sort of philosophical and sort of skeptical.
Great.
I've seen a lot of talks on deep network problem solving, and there seems to be a sort of a bias that the problems being solved are problems that the researchers are choosing to solve because they know a priori that this problem can be solved by the network I'm using. And it may not be the real problem. Autonomous vehicles are big in the news. Machine vision, navigation, collision avoidance, something like that. I saw a presentation, it might have been the Mobileye people who were bragging that using deep networks, they had trained their Mobileye with 1,400 different models of cars that it shouldn't hit. And for each car, what it looked like from the front and the back and the sides. And as long as you were driving on a surface that had nothing but these models, you wouldn't run into any of them. And then the Tesla ran underneath a truck and had the top of the car shaved off in Florida last summer. And I heard an expert say clearly Tesla was negligent because they didn't train it how to recognize trucks parked sideways across the highway that it shouldn't drive under. But the next training set will clearly include that as something they'll teach it not to hit. That can't be the way life forms work. A bird doesn't keep flying into vehicles until it learns which vehicles not to fly into.
Yeah.
Is there some lack of reality or practicality or asking the wrong questions that may be infecting your whole discipline?
Oh, first, that's a very deep, good philosophical question. And I don't know how well, like, how long it's going to take to get those systems to the level of accuracy that we're really happy with in terms of having enough training data and being able to drive it in a way that we're all happy with. I'm pretty certain that they don't drive in a human-like way currently. And I think some of the ways that people drive and analyze the scene would be really useful if we had those in those systems, right? And so it's, again, some of this causal principle in terms of looking at the scene and understanding why is it there and what's going on. And if you see someone running into the street, like a car is very good at detecting a pedestrian, and it'll stop and say pedestrian, but it doesn't go the step further to try to say, why is the person running to the street? Are they not looking? Are they chasing a ball? And those types of inferences, figuring out like what the person's belief is, what they're trying to do, whether they're paying attention or not, are very automatic and very important part of our perception. And I think they can be very important for making predictions and understanding what to do in a scenario like that. And so I think looking to people there, again, could be helpful in sort of making systems that can do well in those edge cases that the training data may not represent well.
A polar bear does not look anything like a pedestrian.
Yeah.
Nor does a football player in uniform.
Uh-huh.
But you don't want to run into them either.
Yeah.
But you do want to run into zombies.
Okay, zombies, I'll give to that.
These look like people.
I mean, this is sort of a cliche, but people think about people as having brains that are a pattern recognition analog thing, half, and another half that's analytical. You could look at a machine vision problem as what are the characteristics of everything you don't want to run into? And you might get there eventually by feeding it hundreds of thousands of things you don't want to run into until you've exhausted them all. Or you might think in terms of how does any solid object cast an image on the retina, and what are the qualities of getting closer to a solid object, no matter what color it is or anything else.
Yeah.
Now, what's inherent in things that shouldn't be there? And might the real solution for such things attack each problem from both directions, strictly analytical and strictly pattern recognition, and try to come to a synthesis, which supposedly is how brains work.
That sounds like a great idea. Yeah, I think that the intuitive understanding of the physics of a scene is, again, very important and very cognitively natural. And being able to combine that with the data-driven pattern recognition approach would be like a very good idea. So it seems like most of the work is very heavily on the pattern recognition side, but that seems like a great idea to me.
We can talk about that over dinner.
Cool. Well, let's let the video guy run, and then we can find out what's really true. Let's see the advantage. Thank you very much.
Particular domain. So the domain we picked is handwritten characters. And if you're a machine learning person, you almost certainly know about the MNIST data set, which is a standard benchmark. And in terms of concept learning, there's 10 concepts, which are the 10 different digits, 0 through 9. And there's 6,000 training examples of each of the digits in this data set. And we have a new data set, which we call the Omniglot data set, which you can download on GitHub if you want to try it out. And we think of this as the transpose of MNIST, or the more human-like version of MNIST, because rather than just have a few concepts and a lot of data points for each one, we have many different concepts, 1,600 different concepts, and 20 examples of each of them. And the concepts are picked from 50 different alphabets, some of them real, some of them synthetic, and there's just a small number of data points for each one. So I showed you these interesting things you can do with a concept like a segue. And it turns out you can do a lot of these interesting rich abilities with simpler concepts like a handwritten character. So first of all, let's see if you can learn a new character from a single data point. So everyone take a look at the image at the top of the screen there. And in the grid below is another example of that character written by somebody else. So I'm going to move my laser pointer across the screen, and I'm going to ask if you could clap your hands if I touch another example of that character. Is everyone ready? All right. So that was some excellent one-shot learning. You clearly didn't need thousands of images. Just a single one is enough. And in addition to doing classification from a small amount of data, you could also parse it. You know about efficient ways you could produce it. You could generate your own examples of that letter. You can even generate a representation. You can use it to parse an object into its most important parts and relations. You could use it to generate new examples. You could sketch your own version of a segue. Or you could even generate a new concept. So if you take a Segway and a motorcycle and a unicycle and combine them together, you could think up or imagine new types of vehicles like the one on this slide. So how do people do this? How do they learn rich concepts from small amounts of experience? And it's interesting to contrast this with some of the biggest breakthroughs in machine learning and AI, particularly in the space of object recognition, where we have these deep neural networks that are trained on very large amounts of data. So this is the famous AlexNet deep convolutional neural network. And it's trained on the ImageNet task, which has 1.2 million images and about 1,000 images per class. And the model is very large. It has 60 million free parameters. And below, I'm listing some of the more recent versions that won the ImageNet challenge in the years after AlexNet. And these models are trained on very large data sets rather than on small data sets. And also, their primary focus is on classification as opposed to some of the other abilities I just had on the slide. Yeah?
So a common thing with deep learning is most people with deep learning give very nice, curt, cute test cases. You can show pathological cases as well too. I mean,
yeah. In one of the case studies I'll go through, I'll show some stimuli that they don't seem to match people's judgments. And the second part, which is going to be shorter, is going to be about asking questions. And I'll give you a little teaser about what I mean by this. So when people are asking questions while learning, this is a form of active learning. And if you imagine you're a child and you're learning about different types of instruments, and you have these objects in front of you, you might ask questions like, and you don't fully understand how instruments work yet. You might ask, how does a saxophone make a sound? Or what's the difference between the second object and the third object? What's the difference between a trumpet and a horn? Or what features are especially important about a French horn? And in contrast, there are active learning systems in machine learning. So are you ready for what the standard robot questions look like?
What's it made of?
Nope. So most of the time in active learning, the question has this form: what is the category label of this object? And what is the category label of this object? And what is the category label of this object? And I'm being a bit unfair. There has been interesting work in active learning and robotics about asking richer types of questions, but I think it's fair to say that we have no algorithm that matches the sophistication and the richness of the human ability to ask questions when learning new things. So here's the outline of what I'm going to talk about today. In concept learning, I'm going to go through two different case studies, one on handwritten characters and the other on recursive visual concepts. And then I'm going to talk about a third domain, which is active learning with richer types of questions. The title of the talk is Concepts and Questions as Programs. And by programs, I mean expressions in some structured description language that's a lot like a programming language. And we're going to think about what the structure, can you represent each of these domains with a form of program? And what is the structure of those programs? What are their semantics? And that's going to be one of the unifying themes across these different domains. But I want to add a disclaimer that by the end of the talk, there isn't going to be a single piece of software that you can run out of the box on many different types of data sets. So the main goal is to try to study the principles and the representations that people might use to solve some of these problems. And I'm Brenden Lake from NYU, and my talk is called Concepts and Questions as Programs. So as Andy mentioned, I'm a cognitive scientist, and I study computational problems that are easier for people than they are for machines. So there's been a lot of exciting recent progress in AI and machine learning, yet for most types of everyday cognitive abilities, people are still better learners and thinkers than machines are. And by everyday cognitive ability, I mean things like concept learning, asking a question, understanding a scene, or tasks that involve creativity, general purpose problem solving, reasoning, language understanding, speech recognition, and so on. And my research has two main goals: to better understand people and also to try to build a more human-like learning capacity in machines. And today I'm going to focus on two of the abilities on this slide. I'm going to focus on concept learning and asking questions. For concept learning, for me, the motivating question is, how do people learn such rich concepts from very little data? Imagine this is your first time seeing a segue. You just see that image of a segue at the top of the screen. That single image might be enough information for you to basically get what the concept of a segue is. And you can recognize it again, even if its features or its appearance have changed, and be able to rule out other distractors that share some properties in common with the original image. So this ability is often called one-shot learning, and it's been of interest to cognitive scientists and AI researchers for a long time. In addition to learning very quickly, people also seem to learn very rich representation. So by the time that you can recognize a segue, you can do many other things with that concept, with that mental. Use that to inspire more human-like learning algorithms, but it's still going to take work to try to use these ideas and these algorithms in different types of domains. So it's not an out-of-the-box approach yet. And there's an alternative title for this talk. Instead of about concepts and questions as programs, I could have called it or named it after these three key principles that are going to thread through the different case studies that I talked about. And these principles are compositionality, causality, and learning to learn. And I'm going to tell you a bit more about what I mean by these different things. And I think learning programs is a very natural way to implement these different principles together in a single type of computational approach. But the principles are more general than this particular approach, and you can imagine integrating them into other types of machine learning and AI paradigms. So this is the other way you can think about some of the ideas here. OK, so let's get into the first case study, which is about handwritten characters. So this work is joint with Josh Tenenbaum and Russ Solokhudinov. Josh is at MIT, and Russ is at Carnegie Mellon, and it recently appeared in the journal Science. So reminding you about this question, how is it that people learn rich concepts from very little data? We wanted to study this ability, and we wanted a testbed domain that had certain characteristics, where we wanted the concepts to be natural and high-dimensional and have enough structure of real-world objects, but we also wanted them to be simple enough that we had a reasonable chance of building a computational model that could see most of the structure in the stimuli that people can, and we could compare people and machines on a roughly even footing. And we also wanted a domain that could help us generate insights that were more general than that.